All right, good morning. Hope you all had a good spring break. As we talked last time, we met in person. The immediate previous class meeting we had was through a recording, so we did not do it live. I asked you all to start watching or to watch a video where we started this terrain properties exercise. So I'm assuming you all did that. If you did not do it, then I'm not sure you're going to be able to follow today. But I did ask you all to follow it. So I guess the assumption is that you all did. All right. So for us to get or continue with this exercise here, I ask you to open your 08 terrain project that you had to create in the beginning of this exercise. Just, I guess, let me show you quickly here how that looks like on my side. But all these instructions for these I sent on the email before you watch the video. This is how my class folder looks like. You should by now have the 08 terrain folder inside of a class folder. And if you go inside of it, you should have terrain, code, data, terrain project, then subfolders, code, data, and output. And I did ask you also to move your partial code that I share on GitHub to the code folder and your 08 elevation.csv into the data folder. So I am assuming you're all set up with this. If you're not, unfortunately, we're not going to have time to wait, as this was part of the previous lecture or video that I shared. All right, so what we're doing here on this whole exercise is really the goal is to bring elevation data and use that to create secondary variables. Elevation, along with some other layers that we have, it's going to be a really important piece of information for us to understand yield patterns, both within a given year, but also across years. So that's why we're bringing this layer. In this case, I guess a difference from last semester, so maybe something I did not mention in the video you all watched, is that this elevation data we're using is actually coming from it was actually collected with a GPS in this field. I'm not sure what was the equipment that collected this elevation data, but we do have it being collected from the field, which is different from the open data exercise we did. That elevation data set was not collected on the field. It was coming from probably some type of radar or LiDAR type of mission that was probably done, definitely not on that field, but some other way. So in this case here, we're following the case of you had, this grower here had on this field some type of equipment that had GPS that was collecting elevation or height or elevation data here. And we're going to use that to create a digital elevation model, which is then the basis to calculate a lot of other terrain variables. All right, so right now my environment here is empty. I don't have anything there. So I'm just going to make sure I run all the chunks to get to the point where we stopped on the video. Here I was just setting a theme. I mean, this is just something I wanted to show you in case you want to do it. If you have a specific theme that you want to apply to multiple plots, you can create that theme and just call that later. This is not necessary. It's just a way to help us to be more efficient with our coding. So we bring in that elevation data. One difference here from the video that you watched is that the name of this elevation data set, the CSV here, is different in the video from what we have in class. So in case you had trouble there, I hope that you are able to realize this. Just quickly looking at this, we have about 55,000 data points in 5 columns. So we have an object ID, a point ID, grid code, point X, point Y. And in this case here, it is perhaps, a great example of why it's good to name our columns with short yet informative names that hopefully contain the units. Right now, what I'm going to tell here is that this grid code column is the actual elevation in feet. But if you're getting this data set here from someone else, and maybe that person is not even, I don't know, reachable anymore, you could make guesses here, right? But still, I hope that you can appreciate the fact that having properly named column names is important for you and also when you share data with others. All right, so we did quick wrangling here. So we just clean names. We renamed that grid code to elevation feet, transform elevation from feet to meters, selected the meter, point X and point Y. And up until this point, so the quick reminder, this is a CSV on your file system. This is a CSV file. So it's not a geospatial file yet. So we bring it here because we do have those columns. We have two columns for the coordinates. We can transform this into SF or into a vector geospatial file by saying that those columns contain your coordinates. Then we need to set the CRS. Remember that, so if we just run, I'm just going to quickly run this to remind you, this is an important part with any geospatial data, regardless of the software. But in R, the way that we see that is if I stop right here, just using the SC as SF, I see that there's no SF or there's no CRS assigned, and we have to assign a CRS. If your layer does not have a CRS assigned, you use the function stSetCRS. If it does have a CRS assigned, but you want to change what that CRS is, then you use the stTransform. Make sure you understand the difference between these two functions and when they're used. So here we're assigning a CRS, which is the WGS84, and then transforming that CRS to a metric system CRS, which is UTM N8083, zone 16 north. Right? So if we get a summary here, we see that elevation on this field in meters was changing from about 45 meters to about 54 meters. So there's a 10-meter gradient across this field. We did this quick plot here, and I'm just showing you how we were plugging the my theme map that we created above in the chunk. This is how we would do that. Just to, it is basically an object that contains some of the settings that we selected. This is that elevation map. This is the next chunk here is going to be another difference as well. So, all right. So even though I think in class I did something like, on the video. So right now, this layer that we just plotted is that LFW object that we created above, which is a simple feature collection of type point. When we make this plot here, it looks like a continuous layer, right? It does not look like a point layer. The reason is that there is a very high density of points that they look like it's continuous. I think in class, the way that I showed you, just for us to, I guess, double check that this is actually point on a map would be, I think I did ST simple perhaps, and then see what are the arguments here. Let's try size equals 600, which I believe is going to take only 600 points out of the 55,000 and plot them. Sorry, what was that? What was that? Simple underscore. Oh, yeah. Wait. So not ST, so it's just simple. Oh, yeah, that's right. So then we can take let's take 0.5% or 50%. So 0.5 here, so that works. Yeah. So now, yeah, thanks, Joel. So we use this function sample frac for sampling a fraction of the data set. I'm going to change this to 0.1 just to make it more. So only sampling 10% of the points. We do see that these are points, right? It's just that it's such a high density layer of points that they don't look like it. Yeah. This one?
Yes.
I think that I showed, but also removed afterwards because this is just for visualization, right? I don't want to carry on with just 10% of the data points. Yeah, so if you If you want to copy that, you're welcome to. If you also want to just deactivate that, that also works. Because in the end, that was just a way for me to show you that this is actually just like a proportion of the points, and to show that they're actual points and not polygons like they may seem if you run with all of them. All right. So the next step here that we were doing was to import the boundary. This was a different path from what we had in the video. I hope that you were able to realize that. So here the boundary is going to be in your 05 digitizing project output, and then boundary GeoJSON. So if you just run that, you should have this boundary underscore W object with being transformed to UTM zone 16 north as well. Okay, I just want to stress this point again. Every time you're doing interpolation, regardless of what type it is, in our case is inverse distance weighted. If it is any type of interpolation, you will need a grid, right? So the reason why we're bringing the boundary here is so we can create the grid that we're going to use to do the interpolation, right? So we have already done this in a previous exercise, so that's why I left you basically all the code there. I don't think there's anything for you to do, or maybe we did this already in the previous video. But anyways, we're bringing the boundary, creating a grid of cell size 10. A reminder here that's important. If you are doing an operation in a geospatial vector file like we are here, and that operation depends on distance, like we're doing here, right? So we're doing interpolation. Interpolation depends on the distance between points. So it is a distance-based operation. You want to have your layers being already or being transformed into a CRS that has meters or has a distance as the unit. You do not want to bring in here an object that has a CRS that is in degrees, like WGS84. The reason for that is sometimes it may work. Some functions that use some of these ST functions may still work if you're using WGS84 for a distance-based operation, but they may also fail miserably. I think this would be a case here that, because what happens is on this function ST make grid, we say cell size equals 10. This 10 here is in whatever units the CRS of boundary W are in. So if I say 10 and this is in UTM, then it understands 10 meters. However, if this is in degrees, it may understand 10 degrees, which is vastly different from 10 meters. So just for you to keep that in mind, if you're doing distance-based operations and using geospatial files, make sure the CRS is in meter or even feet or any actual distance metric and not degrees. All right. So just creating the grid again, we printed on my side. Let's see here. I guess it's not, well, I guess let's just make this plot here and we can take a look at it. This should be the similar grid of what we have done before, right? We're just redoing the same grid in this case. And then I believe this is where we stopped. So our next step here is, so we brought the elevation data. Even though it's a high density elevation data, it's still not continuous, right? If you really think about it, anything that you have at least a couple points, even if they're very far away, if you zoom out enough, they're going to look like they're connected, right? That's kind of what's happening here. If we were to zoom in, we would see gaps between these points, right? I mean, if we don't sample, I guess. If we zoom in enough, we would see gaps between these points. So that there are gaps because this is a point data layer. So we do want to make this continuous by interpolating. Okay, so if you come here on the next chunk, we're going to do that interpolation. If you remember to do interpolation, at least the way I'm showing you, we have to do that in 2 steps, where the first step, we set up the formula and the data. And then the second step, we predict that formula in data onto the grid that we created. So the first step here, if you recall, we were using this function called gstat. And it has this argument here called formula, where it's basically going to be, so, well, let me just print here quickly, elev underscore w. This is the object that we're going to interpolate. So if you come on the data side, it has this column called elev underscore meter. So this is what we want to interpolate. So this is what we say, elev underscore meter tilde 1. So we're basically saying that we want to interpolate this column. This is important because maybe this data set here, in our case, it only has 2 columns, but if it were to have more columns, you have to specify which one of those have the data that you want to interpolate. And then you add a comma, you return a couple times. We need to say what's the data where this column is coming from. So on the data argument, we say elev underscore w. So if you run that, and then you just print that IDW mod object that we created, really is just setting here the formula and the data set that we're going to be interpolating, but IDW mod is not the actual final product yet, right? So now the next step on this 2-step approach is to actually predict IDW, what was that called? IDW mod onto our grid. So if you come here on the next chunk on the IDW pred, we're just going to use this function called predict. And the first argument we give it is the data set that we want, or the object that we want to predict, which is the one we just created above, IDW mod. And then the second thing here is to say what is the grid that we want to interpolate, which is an object that we created above called grid underscore R. Just to remind you, so whenever we're predicting on this IDW mod, we need to give it a grid, and then our grid has this underscore R in its name to represent that it is a raster. So it needs a grid as a raster to work. If you were to give a grid here as a vector, it would not work. The way that we are making that work, or the way that we're making sure that's happening, is if I just come back here on the grid R code. So we're bringing the boundary, making the grid right here. If we were to stop, I guess, until here, this would be an SF object, meaning that the cells of this grid would actually be considered as polygons. We do not want that. We want these to be seen as a raster cell, right, instead of a vector polygon. So that's why we use the ST rasterize, and then we cropped. We already went through these steps in the previous class, but I just wanted to show call your attention to this, that this function ST rasterize is what is turning this grid from vector to raster, and we need it to be in raster to be able to interpolate. All right, so if you my side. Don't have a left W. I do have it. So like a W mod. I'm not sure why I'm getting that problem. Is anyone else getting an issue here? No. Maybe maybe it's getting the function from a different package on my side. Load use that again. Oh, maybe I didn't. I think I did. Okay, let's try again. I'm not sure what's going on here. Predict gstat data. If anyone else online is having this issue, let me know, because if it's just me, maybe
I had it also. Yeah, me too.
You also have the issue? Oh, yes, Neva got it. Thanks, Neva. Yes, everyone, sorry. So when I was typing here, actually, I think, so Neva said that maybe here on the GSTAT formula, it should be LFM, and I by mistake gave the data set name. So the data set is called LFW, but the column is called LF_N for meters. I think that's it. Let's try again. Yours is not working. So on my side, it worked. So you actually solved my issue. So you have LF_M on the formula? Yeah. Yeah, so sorry, when I was typing, I may have confused you all. Here we want the formula should be the column name that we are interpolating, and then the data is the data name. And I got confused on my side. So LFW should be the data, but on the formula should be LF_M because that's the column name on the data set. So if you all fix that on your side, it should work. If it is still not working, let me know. We can troubleshoot it, but it should be working out. So IDW mod worked. My IDW pred ran as well. So basically making a prediction for each one of the cells based on the data that we gave it above. If you just run IDW pred, that is a stars object. And a stars object, we talked already about this, but it basically gives you two columns here. One is var1 pred, which is the predicted interpolated value for each one of the cells. And then it gives us a var1 var, which is the variance of the prediction. In the case of IDW, we do not get a variance of that prediction. You would get this column populated if you were doing any type of kriging, which we're not. All right, so after interpolating here, I want to visualize this. Again, in R or in any programming language, if you don't ask for a map, you don't get one, which is one of the differences between using ArcGIS or QGIS or other point and click softwares, which you always get a visualization. So let's create a map here. I left you a beginning of it, so I want to create a ggplot to show this interpolated map, and I'm assigning that to this object called the left map. So I'm leaving empty at the level of ggplot because we're going to be bringing a couple of different data sets here. So if you just add a plus, hit return. All right, so let me ask you this, and I do hope that you're thinking about this because it's simple, yet it's important for me to know that you are getting this concept. I want to make a map where the first data set I want to bring is IDW pred. What type of geom should I use here? What do you think, Doug? Okay, so Doug said geom SF. It is, for now, I'm just going to say it's not SF, but I'll tell you why after someone tells me what it is. Neva, geom stars, right? So, okay, here's a quick way of knowing that. So this case is geom stars because IDW pred, which is the object that we want to plot, is a stars object, right? So if you printed it and you come here, it says stars object. Another way of you to check it is if you use the function class. So remember, this function is very useful for you to learn what is the class of that object. If I ask for a class, it is of type stars, right? For example, if we were bringing the boundary, you can get the class of it. The boundary is SF, right? So boundaries, points, lines are simple features, are vector geospatial files, and we're using this SF package to handle them, so they become SF objects. In this case here, we're going to use geom stars because the object that we want to plot is a stars object. So we say data equals to IDW_pred. Let's just run that and see how it looks like. All right, so if we run it, it just looks like this. So we do have the var1 pred, which is the predicted elevation meters on this site. the next thing I want to, and if you recall, for some reason, stars objects, when we plot them with geom stars, they don't really set the coordinates in a way that it looks like what looks on the field. But when we bring SF objects with geom stars, it does. So I want to bring our boundary here. So let's add a plus. Now, what geom do we use for the boundary? For Nelisa, what do you think? SF, right? So the boundary is SF. Let's use geom SF here. Just say data equals boundary underscore W. And I just want to give a comma here and say fill equals NA. So we can see through it and it doesn't hide the first layer that is IDW pred. All right, so if we bring the boundary, then it looks like this. It kind of sets your X and Y coordinates to be proportional instead of like extending them as it was done before. Okay, a few steps here I want to do, and I always want you to think about this. If I'm asking to create a publication ready plot, I do want you to look at this and think, is this something that would fly if I submit for a journal to be published in a paper? If not, then address the shortcomings. So one of them here would be, well, I guess you could submit with this color scale. That would not be an issue, but I always want to have a more inclusive color scale. So let's use a colorblind safe color scale here. So add a plus. Let's use scale underscore fill underscore Virides underscore B for bins, right? So now we create bins instead of having a continuous. And I do want to change the option. So I want to do option equals uppercase E. So this is how that will look like. Something I want to call your attention again, because when you do this on your side, I do want you to be understanding what you're doing. So I guess one difference here that I don't know if you notice, but with geom stars especially, if you only have one column in the data set, well, I guess we actually have two here, but it is choosing the first one to assign the fill. So notice that on geom stars, we did not even need to say comma AES fill equals var1 pred. You already did that by default for us. If you did not want var1 pred to be your variable for fill, then you would have to manually come here and say AES fill equals that. So that is one thing that geom stars does that other geoms don't. And because of that, it's implied that fill is what we're changing here. And it is what we're changing because raster cells have a fill. So that's why on the scale, when we want to change the color scale, we use scale underscore fill and not scale underscore color. If we use color here, I don't think it would have worked. Just to show you. Right, so it did not work because it doesn't have any aesthetics mapped to color, just to fill. So every time you change something in AES and you want to further customize that, use a scale underscore, then whatever you're changing on AES, and then whatever options you have with that. Here, again, with geom stars, that is implied, but it only happens with geom stars. So all the other geoms we've been using, you have to explicitly say AES fill equals to variable name or column name. So just wanted to make that quick parenthesis here. All right, so the next thing is I want to change this var1 pred title of the legend. We've done this a couple times, so I want to ask someone else that hasn't helped me yet to tell me how do you think that we could use this? Let me look for someone online here. So my goal is to change this title here. We've done this a few times, so hopefully you all are already familiar with that. So let's see, Kumar, what do you think? How do we change? What function do we need to change this?
I think we're gonna use labs.
Okay, what else?
Ligand. I think we're gonna name it. It is a ligand. I'm unable to remember how do I change the name.
No problem. You got the function right, so thanks for that. Let me see if maybe someone in Tifton remembers what we have to change this legend title here using the function labs. Anything?
No.
I don't remember off my head.
Can you repeat that?
No, we just said we don't remember how.
Yeah, not off the top of my head.
Yeah, no worries.
If I had to guess, I would just rename it to whatever I wanted and then say like equals title, but that's just a shot in the dark.
Yeah, I don't think you got it, but it's a good guess. Anyone knows here before I give you the answer? Phil, okay, yes. So if we come here in labs and you just hit tab, it would show you the options that you have to change. And I guess it's not showing all of them, but it's showing you some of them. But what I want to stress, or not to stress, but just to point out, is because we're changing the fill here in labs, you would call that. So we say fill equals to, and then you give the legend. So it may not be the, maybe you were expecting something like legend title or something like that, which is something you can change on the theme. So we could also change this on the theme. So you guys are all, you're all thinking correctly. So we could change that either in the labs function or in the theme function. In the labs function, we need to say what is the aesthetics that's being used here. So that is the fill. And we just give quotation marks. I want to call this 11 dots and then M for meters. So if we do that, now we change that title right there. And then lastly, I just want to apply our theme that we set in the beginning of the exercise. So if you just add a plus, that is called mytheme_map. And so this is how it looks like. All right, so let me ask someone in class. Yep. So if you're already seeing on your side, and I'll scroll down on my side after you all are caught up, is we have the elevation data binned into a few different bins here, right? So going from 45 to 55 are the bins. So first off, let's just think about where is the point of highest elevation? Where is the point of lowest elevation on this field? So let me ask someone here, Sundance, what do you think? Where do you see the highest and lowest points?
On the left side is corner of the left side.
So on the left side, you have which one?
Highest
Highest points, right? And then where are the lowest points?
on the right.
On the right side. So we have this gradient here going east-west, right? All right, so how do you think where do you think water moves from and to in this field?
From left to right.
From left to right, right? Yeah. Perfect. And I'm asking that because we're actually going to be doing something related to that in this exercise. All right, so highest points on the left or west side of the field, lowest points on the right or east side of the field. So we have this east-west gradient and water is moving from left to right because of that.
I want to ask a question here.
Yeah.
When I'm looking at this picture, I remember when we were reading about where the erosion has been done. The diagram was like the erosion has been more on the bottom, the blue side, and it was coming towards the right side. So I thought the right side is having more elevation.
Well, I mean, from the if we were to look at the base map of this field, we do
Yeah.
see I guess we see some kind of fingers of erosion kind of cutting
Yes.
west, right?
Yes.
Just looking at that, I guess I mean, without knowing the elevation of the field, but just looking at that base map, it's hard to tell if it's going east-west or west-east.
Okay.
We know it's on the east-west direction, but we don't know where it's starting, where it's ending without seeing the elevation, right?
Okay.
So it would be really weird, I guess, if we look at this elevation map, but then we had like those eroded fingers cutting south-north. That would not make a lot of sense,
Okay.
right? But as
Yeah.
far as they are on the same direction of the gradient, then it makes sense. Then it's just more a matter of looking at the elevation map to understand if it's moving from west to east or east to west.
Okay.
Does that make sense?
Yeah.
Thanks, Kumar. Okay, so now with so notice how we needed to have a continuous layer. And when I tell you continuous layer, I hope you think raster, because the raster is continuous, vector is not continuous. Unless you have a whole polygon covering your entire area, which is not the point, right? So we want something that can change continuously in an area. So that's why we need to have a raster object type, which in our case is a stars object type. And that is IDW-pred, right? So IDW-pred, oops. If I just print that again, it is a stars object. It is a raster file type. So for us to now calculate slope and aspect and other things related to terrain properties that are going to be secondary variables that we calculate based on that elevation that we just interpolated. That's the first one that I want to do here is slope. So I left you some code here. So we're starting with IDW-pred, and then we're just selecting and renaming that var1 pred column to 11_meters. And I'm going to show you next what would be the steps that we need to do to get to calculate slope out of elevation. So if you add a pipe here at the end, you can come after this comment. Just so you, and if you come after this comment here and you just hit tab, it indents your code for you in case, you want to be on the right indentation there. So, okay, so here is the thing. We're going to be using the package Terra to calculate the slope. There are a couple different ways you can do this using different packages. I just want to tell you that so you are aware of it. There are different ways of doing this. We're going to be using the package called Terra. So Terra has this function called terrain that we're going to use for this. However, that function terrain from the package Terra only works with objects. I think it's called like a spat rest object type, which is also a raster object type, but it's not stars. So because of that, we are starting here with the stars object. Before we can actually calculate slope, we have to transform this raster stars object into a raster spat rest object. So still two raster object types, just one is stars, one is spat rest, for us to be able to do this. So immediately here, let's use, I want to call the package explicitly. So it's Terra : it has this function called rest. So if we run this and I just print this object called slope, well, let me do the following. I'm going to reprint IDW-pred, which is what's coming in. That is a stars object, which is a raster type of object. If I let it go through to the Terra rest and I print slope again, this is now a spat raster object type. It is still raster. It's just behind the scenes is being interpreted a little bit different. And we need that so we can apply the next function. So just want to call your attention to that. All right, so now that this is in a spat raster format, we can add a pipe here. And also let's call the Terra package to make sure these functions are coming from the proper package. So Terra : it has this function called terrain. where the first argument here is what you want to calculate. So if you just give it a open and close quotation marks and say slope, this is what we want to calculate. Before we really run this, I just want to tell you, I'm giving you these, the code with the functions and the arguments, because I already did this on my side. I know what I should give it. On your side, it's probably a great idea to look at the help of this function. So help terrain. And take a look at the arguments for a second. So I'll just ask for help of that function. So remember that always going to show you the arguments. So here, so it has this, so X, so the first argument is the data set coming in, and here it says that it should be spread raster, right? So that's what's happening here. And because we're using the pipe, remember, the pipe always takes whatever is on its left and gives it as the first argument of the function on its right. So in this case here, it's basically saying X equals to everything that's coming through the pipe before it, which is basically our everything we did above here, right? And then it has this V argument, which is the one we're changing here. That is a character. It's saying that it should be a character, so that's why we're given in quotation marks. And it's one or more of these options: slope, aspect, TPI, TRI Riley, and so on. You can see some other there. So and then it says see details. So if you want to know what these things mean, so first off, these are all the things you can calculate based on elevation from this function. If you want to understand better what those mean, you can see the details here, and then it's going to explain to us how it is calculating those different things and what do they even mean. So if you're using this function to calculate some of these metrics for a paper, for example, you can say that you use this function, and in this case here, the function also provides the citations that provide the people that actually develop these formulas to calculate these things. So if you need citations, you would be able to provide some of these references here depending on what you're calculating. All right, so one thing I want to change here as well is the units. So if we come here and check the arguments, it has this unit argument that could be degrees or radians if the output is either slope or aspect. So I do want to come here and say unit equals to radians per our slope. Okay, so if we go ahead and run this, and I just want to print what slope looks like, it is still a spread raster, but now the values are slope, right? So these are not elevation anymore. These are slope in radians. So a couple of things I want to do here is so we started with stars. I transformed this to spread raster so we could calculate slope, but I want to bring it back to a stars object because that would be the easiest for us to plot. So let's add here a pipe. So if I want to transform something into stars, we have this function here, st_s_stars. So if we run that and then we print this object called slope, now we can see that it has been transformed back to a stars object. And then the last thing I want to do here, so if you add after that STS stars, you add a pipe, and you come after this other comment here, transform into PCT. So I want to basically transform from radians to percent. So I have a slope instead of having as a degree unit, I have that as a percent unit, which I think is easier for us to interpret it. So we're going to create here this a column. So we're going to use the mutate function. I want to call this PCT. And to transform radians to percent, we need to use the tangent of the slope value. So for that, there's a function called tan for tangent, and we just say tan of slope. So that is because we have, let me see here. So when we transform to stars, now we have this column called slope on the stars object. So that's why we're saying tangent of slope, because that's the name of the column of the data set. So it's a tangent of the slope times 100. That is basically slope as percentage. So if we run that and we print it, now we have two columns, one that is slope, one is PCT, and we can see that the minimum slope in a percent unit is 0.02%. The maximum is 7% for this field. Which is, yeah, that's a good point. So if you, I mean, in your case, you would still have similar values, right? I don't expect you to have very different values as far as, especially the minimum maximum, but it would be affected by your boundary. So you would have slightly different values here when you look on your side. All right, and the last thing here, I just want to give it a pipe, and I just want to, because now we have slope in radians and PCT, which is slope in percentage, I just want to only keep the PCT one. So let's use dplyr : select PCT. So something that, so the way if you go on the documentation of this function and you read of how the slope is calculated, what it does is for each one of the cells, or each one of the raster cells. So imagine that you're sitting on a given cell, right? So I'm sitting here, let me come here in front of you all. I'm sitting on a raster cell. So the algorithm looks for all of its neighbor cells, right? So let's say I'm sitting at elevation of 40. So it looks of all the cells surrounding where I am, and it looks which one has the highest difference in slope from where I am. Right, so let's say I am 40, I have 41, 41, 41, and 50 behind me. So it uses the 50 because it's the highest difference and calculates that to give a slope of my cell. And it does that for every cell. Right, so that's how slope is calculated based on elevation. So something I want to, I guess, wrap up here for us to just think about is, so IDW-pred is the one coming in. And let's see. So on var1pred, we had 2162, so 2,162 NAs, but now slope, which is the output of all this, it has maybe, I don't know, 300 more NAs compared to elevation. Anyone has a guess of why that would be? Why do we have more NAs in the slope layer than on the elevation if elevation is being used to calculate slope? What is causing those extra NAs on the slope that were not present on the elevation data? All right, so I think there's just a little bit of things that we have to change here for me to be able to show you why. So I know that we're at the hour. I just want to finish this next chunk here, and then we'll wrap up, and then I'll get your attendance. So I just want to make a map now of the slope data set. So we're using ggplot. We're bringing slope here, and now I want to ask someone else, maybe someone in Tifton. The only thing that we are going to have to change in this code is what geom we're using to show slope. Can anyone in Tifton help me out figure out what is the geom that we need to plot slope?
Is it stars?
Yes, right. So if we just print slope here, that is a stars object. So geom stars is what we need here. So just make sure, was that Clint?
Yes.
Thanks, Clint. Yeah, so geom stars is what we need here. If you just go ahead and run it and print it, this is what it should be seeing on ours, or something similar to that. Let me pull that out so we can have both of them side by side and see if anyone can spot. It's not gonna let me show both. Oh yeah, it will. Okay. So so I have elevation on the left and I have a slope on the right. Can anyone, even though it hasn't updated, I guess, to show us, it's kind of looking squeezed, but as far as what I want you to see, I think you can see. Can anyone spot here what is going on with, like, where do you think those extra NAs are coming from the slope and they were not present on the elevation map? I wish this would refresh so it would show. Maybe do this.
Would it not read the slope if it was on flat? And then.
Okay.
Like not as much.
That is, so if the field is flat, so let's say a given cell is equal elevation all around, I think it would assign a slope of 0. So I think it would still be a number, it's just that the number would be 0.
Is it the map border? It looks like it's a little farther away.
Yes, yes. Who was that?
Dalton.
Dalton, yes. So what's happening here is because for you to calculate slope and aspect and other things we're going to be calculating, you have to have neighboring cells to calculate that, right? So if you are at the border, there are times where you may not have all neighboring cells, and then by default, it just says, I cannot calculate this, I'm just going to give it an NA. So that's why if you see, we have all these empty cells. So on the elevation map, we had cells running all the way against the border. Now the border cells are gone because when it's calculating slope for those cells, it doesn't have all neighbors, so it cannot do the calculation for you, so it gives you an NA. Thanks, Dalton. All right, let's wrap up here. Next class, we'll continue this. And just a heads up, I am highly considering giving a quiz next class. So if you, you know, I hope you were already planning to attend it, but if you were not, I think we're gonna have a quiz next class. So let me take your attendance. Right, the issue is open, make sure you claim your attendance, and after that, we are good to go. If you have any questions, please feel free to speak up. And if not, then I'll see you on Wednesday. All right, thanks everyone, see ya.